In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 68. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with aspects that has to affect on insulation performance of transformers. Best possible selection of dielectric materials is rather to be one of the most crucial designing factor to have a long-term consistent performance and efficiency of a power transformer. Insulation properties of dielectric materials should have been categorized by their respective dielectric strength. Dielectric strength can be referred to the maximum applied voltage required to produce a dielectric breakdown through a material. According to ASTM D149, the dielectric strength of a material is expressed as the voltage per unit thickness, at which the material will conduct electricity. Hence, the higher the value, the greater the insulating properties of the material. Dielectric material is a non-conducting material which can store electrical energy in an electric field. A dielectric material, once it is placed in an electric field, that is alternating electric field, its molecules would have become polarized. This polarization has thus to create an internal electric field which opposes the external field, causing to reduce the overall electric field strength within the material. Dielectric materials with high permittivity can have to polarize more in response to an applied electric field than a material with low permittivity. Permittivity is therefore be one of the most critical property that to characterize the role of a dielectric material. During high voltage designing, selection of dielectric materials that must have the property of high permittivity, as because materials while used for insulation purpose can have to store more energy. Every dielectric material has a definite resistivity, and it is very much crucial so far the insulation design is concerned. Now, resistivity of a material that has to refer as the ratio of the electric field to the current density in the material. So, resistivity is a fundamental specific property of a material that measures its ability to resist the flow of electric current. The resistivity of a dielectric material that would have to depend simultaneously on the number of ions in unit volume, on the charge of each ion, and on the mobility of these ions, that is, velocity under unit potential gradient. These three. Again, I repeat, the resistivity of a dielectric material that would have to depend simultaneously on the number of ions in unit volume, on the charge of each ion, and on the mobility of these ions, that is, velocity under unit potential gradient. In case of dielectric materials, while using for high quality insulator, that should have the property of high resistivity. So, Understanding the concept of transformer insulation aging process and to work out the relative estimation of the crucial insulation life both would have been the most crucial key factor for ensuring the reliable operation of transformers. The insulation aging process is influenced by the factors such as electrical exposure, thermal exposure, mechanical exposure, thermomechanical exposure, environmental exposure. Aging of insulation as of continuous electrical exposure. The aging of insulation under the influence of an alternating electric field would have been developed as a result of twofold phenomena. One, occurring of dielectric losses in the insulation system as due to have the alternating polarization of the dielectric. Dielectric losses must have to depend on dielectric loss factor of the used dielectric material, and loss is prone to be higher with having higher dielectric constants of the material. Number two, incomplete discharges that would have to occur in gaseous inclusions inside the dielectric and between the insulation surface. These two phenomena would continuously lead to enhance the insulation temperature, causing irreversible changes in chemical structure of the dielectric, especially when it is accompanied by vibrations, moisture, and presence of gases in the adjacent medium. The absorption of electrical energy by a dielectric material to have its dipole orientations when the material is being subjected to an alternating electric field is termed as its dielectric loss. However, the extent to which dielectric material is polarized, that would have to depend on electrical frequency. It is important to note that the material's dielectric constant is also be of frequency dependent. Most important. Material's dielectric constant is dependent on frequency. But material's dielectric strength that would have to depend on certain specific composite factors such as chemical composition, molecular structure, impurities within the dielectric material, temperature, ambient conditions, electrical frequency of the applied field and its duration, etc. The insulation parameters that would have to deteriorate because of continuous electrical exposure to the insulation system. For any electrical equipment to design, it is imperative to note that the dielectric strength of insulation system would usually be correctly identified on the basis of a comprehensive statistical analysis under a specified electrothermal exposure to extreme condition. Under the action of the electric field, even at prescribed operating voltages, there would also have the possibility of experiencing electrical stresses on the insulation system, which is also to be characterized as a dielectric stress. Dielectric stress, while developed at any point, is referred to be a potential gradient electric intensity at that point. And that leads to have temperature rise, causing a point-wise local overheating at the insulation system. Such occurrence would then to instigate a gradual process of ionization of gases that are being rather trapped in the gaps of the layered insulation system. There might have been some occurrence of incomplete discharges in gaseous inclusions inside the dielectric, causing to occur a partial discharge when one part of the insulation cannot withstand the respective electrical stresses as experienced and thus leads to flashover. Though a partial discharge is only a very weak partial breakdown in one part of the winding insulation, but as its contained gases are already being in ionized state, so the potential gradient of that part of insulation would have to drop down quickly. At the same time, the current pulses as generated that would force to equalize the remaining electrical charges in the remaining part of the insulation. The dielectric constant of a material that would have been affected by the strength of the applied electric field as because molecules of the dielectric material would have become polarized when the material is placed in an electric field. The material is in polarized state, which means the electrons in the material are be in aligned state with the direction of the electric field, and that allows the material to store electrical energy in the form of electric field. Again, I repeat, the material is in polarized state, which means the electrons in the material are be in aligned state with the direction of the electric field, and that allows the material to store electrical energy in the form of an electric field. Such polarization of most of the dielectric materials is directly proportional to the applied electric field strength. However, the amount of electrical energy that can be stored in a material is typically related to its dielectric constant. If there be any change in electrical distribution within the molecules of the dielectric material as due to have variation of applied electric field, then there would have to change the value of dielectric constant of that material. Material with higher dielectric constant would thus to act as better insulator possessing a higher electrical breakdown strength. Material's dielectric constant is affected by the underneath factors. First, frequency. Dielectric constant has to decrease with an increase in frequency of the applied electric field. It is as because the molecules do not get enough time to align and polarize at higher frequencies, while at lower frequencies, the molecules have more time to align and polarize. Most important. Temperature. Dielectric constant increases with an increase in temperature, and that would happen till it reaches a transition temperature. Above this, any increase in temperature that leads to a decrease in the dielectric constant. Density. Dielectric constant of a material is inversely proportional to its density. If density of the material would have been decreased, then its dielectric constant gets higher. Pressure. Dielectric constant of a material is also affected by pressure. As the pressure increases, the dielectric constant decreases. The electrical properties of a material that can be denoted by the two important parameters. One is dielectric constant, that is epsilon, which is a measure of how much a material can store electrical energy, and electric susceptibility, which is a measure of how easily a material can be polarized. Now, dielectric constant epsilon is an intrinsic material property discovered by Michael Faraday in 1836. The presence of impurities, if any, within the composition of parent molecular structure of the dielectric that can cause to disrupt the usual process of alignment of its molecules during polarization. Most important. Such occurrence that would lead to reduce their that is molecules ability to store electrical energy, causing an effect on dielectric constant of that dielectric. So, dielectric constant of a material is quite dependent on its molecular structure, as because that would have to determine the polarity of the molecules, which in turn affects their ability to align with an applied electric field. Temperature. Temperature would also have a significant effect on the dielectric constant of a material. It is as because if there is any increase of thermal energy due to rise of temperature, that would cause the molecules in material to vibrate more, which leads to reduce their ability to align with an applied electric field. At low temperatures, dielectric generally would have a higher dielectric strength and thus to have less likely to cause an electrical breakdown. The dielectric strength of a material would therefore be decreased with increase of temperature, causing to create partial discharges, which thus to instigate an electrical breakdown of the dielectric. So, it is important to consider the significance of the temperature effects while designing and selection of dielectric materials. So, it is important to consider the significance of the temperature effects while designing and selection of dielectric materials for the equipment of specific purpose application. Specific purpose and application. Oil impregnated cellulose based items such as paper, that is craft paper, pressboard, tapes, and clothes, as would have to provide excellent dielectric strength and low dielectric loss. So these items are widely used for designing the main insulation system, even in case of higher rating transformers. Though water has a significantly higher dielectric constant than that of those oil impregnated cellulose based items, but through diagnosis, it has been exhibited that their average dielectric constant would not be notably affected even if contaminated with a relatively small amount of moisture. The combination of paper and oil that has to produce a composite insulation system having a dielectric strength greater than that of either of the two component materials, and probably the dielectric of such combination is in widest use in high voltage applications up to about 345 kV. In dielectric heating, the amount of heat produced is directly proportional to the supply frequency and the square of the supply voltage. However, oil impregnated craft paper would have limitations in making the insulation for use at exceptionally high voltages, that is ultra high voltage or extra high voltage, right? Mainly ultra high voltages. So, material selection for high voltage winding insulation is the most crucial factor during high capacity transformer design, as because the insulation materials that would always be in various stresses, which include electrical, thermal, mechanical, chemical, and environmental factors. In the course of time, these stresses would thus to intend for causing physical and chemical changes in the insulation materials, leading to have gradual deterioration of their dielectric properties. Transformers with mineral oil impregnated paper insulation, whose dielectric strength is quite dependent on the thermal, oxidative, hydrolytic, electrical, and mechanical condition which transformer experiences during its total lifetime. Accelerated electrical and thermal stresses, these two would be the most significant factors to degrade the strength of the paper interfiber bonding. These two means accelerated electrical and thermal stresses. These two would be the most significant factors to degrade the strength of the paper interfiber bonding. It is to be noted that the paper insulation used in transformers as solid insulation is the polymer of cellulose, which always may have to contain a fraction amount of natural humidity. The aging mechanism that would further to be accelerated due to the presence of water and oxygen in the insulation system. When solid insulation degrades under continuous electrical and thermal stress, it releases cellulose particles in the transformer oil. Transformer oil starts to grab the disintegrated and dissociated cellulose substances, which leads to undergo a natural aging process of the oil with its chemical decomposition. However, formation of oxidation byproducts gets started in oil whenever it has been exposed to oxygen and high temperatures. These two, oxygen and high temperatures. These byproducts, such as acids and sludge, can intensify the oil's aging mechanisms, which significantly impact on its insulating properties to degrade, causing to reduce its overall effectiveness in isolating the transformer's core. As of functionality, transformers are usually subjected to have continuous thermal stress, causing the insulating oil to experience severe temperature variations. Prolonged exposure to thermal stress and high temperatures that would have to accelerate the breakdown of oil molecules, which thus to enhance the formation of carbon deposits. So, formation of carbon deposits in oil is therefore be the collective effects of moisture, oxygen, and heat. These three items, moisture, oxygen, and heat. And that can have to impair the dielectric strength of the oil. Transformer oil is thus to act as a critical component of ensuring the longevity and optimal performance of transformer. Solid insulation in transformers includes kraft paper, Nomex, and pressboard. While combined with oil, then the paper oil composition dielectric strength would have to enhance up to a level of 23%. Any change in physical, chemical, and electrical properties of the oil that can have to degrade its dielectric capability, but also may have to affect its usual heat transfer ability. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.